Okay, in this video we'll be talking about two things. We'll be talking about Euler's form. Okay, we're talking about a new form that we can use to represent complex numbers. And we'll also be talking about something called de Moivre's theorem. Okay, but let's start with Euler's form. Leonhard Euler. Okay, this is a man's name. This is Leonhard Euler, and this man was a very, very famous mathematician. He's called the mathematician's mathematician. And he proved that the polar form that looks like this, he proved that this polar form could also be written as this form. Okay, and the way he did that was by proving that this e to the I theta was actually the same as cis theta. Okay, so he proved that this is equal to this. This is cis theta over here, right? Okay, and we won't go into the proof of this because it requires Taylor polynomials, which is an advanced calculus concept that we'll learn later on in the course. But for now, just know that e to the I theta, where I theta is the exponent of e, is the same as cos theta plus I sine theta. Okay, that's not very intuitive and it doesn't make a whole lot of sense right now, but we'll show that mathematically that can be proven later on. Okay, and this form, okay, so we have polar form here, and this form, if we replace cis theta with e to the I theta, that results in a new form called Euler's form. Okay, and this is the Euler form of a complex number. Okay, so now we have three forms. We have the polar form, we have the Euler form, and we have the rectangular form. Just remember e to the I theta is equal to cos theta plus I sine theta. Okay? All right, so let's look at an example here. It says evaluate e to the negative I pi over 4. Okay, so this is obviously in Euler's form. So if we can write this in maybe polar form or in rectangular form, that would help us. So how do I do this? Well, we know that e to the I theta is equal to cos theta plus I sine theta, right? So in this case, it looks like if I can make this look like this, then I'm good. So this would be I to the minus pi over 4. That's really what's happening, right? So this becomes cosine of minus pi over 4 plus I sine of minus pi over 4. Okay, and once I have this, now we can figure out what the components of this would be. The component form would be minus pi over 4 is down here, and it looks like this is going to be a length of 1. This is going to be a magnitude of 1, right? Because this whole thing is cis theta, and the magnitude in front is 1. Okay, this is a 1 here. And so this would be root 2 over 2, root 2 over 2. And we're left with root 2 over 2 plus or minus. This would be minus because it's going down, so minus root 2 over 2i. Okay? Evaluate I to the minus I. This one looks a little bit stranger since we haven't seen I being raised to the I-th power. All right. Let's think about how we could do this given what we know. All right, so what do we know? We know e to the I theta equals cis theta. All right. We also know that I can be written in polar form. Okay, what does I look like in polar form? Or in in polar form it's up here, isn't it? That would be the imaginary axis. Here's the real axis. So it'd be pi over 2 would be the argument. And so we could say this is cis of pi over 2. Okay, cis of pi over 2. Since we can write this as cis of pi over 2, we can now write this in this form, in Euler's form, can't we? So this would be the same as e to the I of pi over 2. Okay, now why am I doing this? Okay, because if I can get this bottom part to look like an e or something, then maybe I can deal with this exponent separately. Okay, And so we can do that. We substitute this since this is I, we're going to substitute this back into here. So we have e to the I of pi over 2 times minus I, right? Because this whole thing is raised to the power of minus I, okay? Using laws of exponents, we get I equals minus I squared times pi over 2. And this just becomes negative 1, so that's plus 1. So we end up with e to the pi over 2. Okay?